So my name is Harald Javier. I'm a PhD student in Villemaisi's group in Lund. And we do a lot of experiments where we look at quantum dots primarily and focus on probing and making these interact with each other in different ways. And what I've been working on is essentially trying to understand how a quantum dot reacts to a high-frequency signal. And the motivation for this is that typically in a lot of our experiments, or in a lot of experiments especially focused towards information as fuel, you really want to make a measurement. And in our system, our measurement that we can make is essentially in whether a quantum dot is occupied or not. So what we do here is we try to measure the charge of a secondary quantum dot using a detector. And our detector is also a quantum dot typically. And the easiest way, or the most straightforward way of making these determinations or detections is by measuring the current through the detector dot. By placing this detector dot in a sort of sensitive region and capacitively coupling it to the second dot, you can get a sort of difference in current based on the state of the dot you try to measure. And this is nice, and you can do some really cool experiments, and we have in the past created, for instance, a Szilard engine and done some proper information to fuel experiments. But we're limited by the bandwidth of the detection. So we can really only measure things that happen on a kilohertz timescale at best. And what we want to do moving forward is to work with rather coupling the detector dot to a microwave cavity and measure the reflection response from this cavity. So we are doing a type of reflectometry measurement on the quantum dot. And what we try to do is then make a sort of coplanar waveguide cavity. These have been sort of studied a bit previously. And they have a frequency range in the sort of several gigahertz range. And we land somewhere around 6 gigahertz, which is quite large for these type of measurements. And in fact, it is such that the energy of the photons in this cavity now exceed the temperature time scale in our systems, or temperature energy scale in our systems. So we can get some interesting effects where we can actually set our quantum dot in such a state that the energy of the photons in the cavity is now the governing energy scale. So it's bigger than the lifetime broadening, bigger than temperature broadening, and so on in the system. And that can give us some non-typical responses in the reflection coefficient readouts that we measure. So essentially what this poster is showing is several different quantum dot configurations and essentially what the high frequency admittance of this quantum dot is. And this helps us better understand what the detector actually shows when we measure something to essentially help us figure out what kind of systems we should be making if we want to get a good signal in our detection. So yeah, that's sort of a summary of my poster.